In this module, I'll show you a simple igneous phase diagram that I'll use to explain chemical changes that occur during cooling and crystallization of a magma and relate it to Bowen's reaction series. Here's the phase diagram, and what you see are three fields. A field on the top that is labeled liquid, that correlates to a liquid magma. A field on the bottom that's labeled plagioclase, and that's solid plagioclase. And a field in between the liquidus and the solidus that's labeled plagioclase plus liquid. That field represents magma with crystals of plagioclase in it. The liquidus line is the line above which only liquid is stable. And you'll notice that it's higher at higher temperatures, the liquid is stable, and thermodynamically that makes sense. Below the liquidus, you have some solids. The other line is the solidus, and below that line, at lower temperatures, you only have solids, so crystals or a rock, if this was a more complex system. And in between the liquidus and solidus, you have a mixture of liquid and crystals. The y-axis shows temperature in degrees Celsius. So this system is going from something like 10,050 degrees to 1600 degrees Celsius. And the x-axis is labeled weight percent anorthite. And so you have AB for albite, or the sodium end member of plagioclase, on the left. And on the right, AN for anorthite, or 100% anorthite, or 100% calcium plagioclase. And this whole system, we will vary the composition of the plagioclase and the temperature as we cool a magma, and it's being held at a constant 1 atmosphere pressure. In this example, the X marks the starting position of the magma. So we're starting at a magma something just cooler than 1600 degrees Celsius, and starting in an initial composition something slightly more than 60% anorthite. So this example is very simplistic. It is a plagioclase melt, and there's only plagioclase in this system. This has an animation that I'll walk you through. This liquid magma is starting off with a composition X, and you can get the composition by drawing a vertical line down to the x-axis and seeing that the composition is 61% anorthite. We're going to cool this magma down to where it reaches the liquidus. As we're cooling down to the liquidus point, it's still liquid. But once it reaches the liquidus, then we start to crystallize out plagioclase. We determine the composition of the crystals that come out of as soon as this system reaches the liquidus by drawing a line, a horizontal line from the liquidus to the solidus, and then dropping down a line to the x-axis where we read the composition of the first crystal. So the first crystal is going to be composition of 87% anorthite. And notice that the crystals, those initial crystals, have a higher calcium to sodium ratio than the liquid that they're crystallizing out of. So the precipitation of the crystals causes the liquid composition to be more sodic as well. Now we'll cool it further, and the composition of the melt and the crystals will follow the liquidus and the solidus. We're cooling and dropping down the lines along the liquidus and the solidus, reflecting the composition of the liquid and the solid, respectively. The ratio of the calcium to sodium in both the crystals and the liquid decreases with decreasing temperature. And the proportion of crystals increases as the liquid decreases as well. To read the final composition of the liquid. So the last drop of liquid has a composition of AN20 about, and the composition of the final crystals has have a composition of 61% anorthite, just like the original composition of the melt at X. So the final crystals in this system are crystallizing out at 61% anorthite. And at this point, the entire system is solid plagioclase. The last thing I'll just point out on this diagram is the last drop of the liquid. That composition can be estimated from dropping down a vertical line to the x-axis here. And you see that there's a composition of about AN20 or AN21. So the final composition of the liquid is very much different from the initial composition. We've gone from about 61% anorthite to about 21% anorthite during cooling and crystallization. So crystallizing out plagioclase has a dramatic effect on the composition of the liquid. You are separating out calcium from the magma in the plagioclase crystals and leaving behind a more sodium-rich magma in the end. All right, what you learned here was phase diagrams can explain the chemical changes during crystallization of a magma, and that the chemistry of the magma changes when minerals crystallize out of it. This explains the continuous series of plagioclase crystallization and Bowen's reaction series, that you see more calcium-rich plagioclases up at higher temperatures on Bowen's reaction series, and more sodium-rich plagioclase at cooler temperatures near the bottom of Bowen's reaction series. And hopefully this will help you understand the solid solution of calcium and sodium in plagioclase. Now I'd like you to go answer the questions about a similar phase diagram for the solid solution of iron and magnesium in olivine crystallizing out of a magma.